When you set up a hammock and you get into it for the first time, you do so with some apprehension. And that's because as you get into it, you can hear the ropes creaking and straining under your weight, and you're really not sure if it's going to hold you or not. By the end of today's lesson, we're going to be able to calculate how much force there is on the ropes that hold you up with the hammock. We did some work in an earlier video with velocity vectors and treating it as a vector, which the length of this is the magnitude or the size of the force. And when this person is pushing in this direction, there is a component in the downward direction and a component in the forward or to the right direction. So when they push with this magnitude of force, that length of a vector, only this much of it is actually being used to do something useful. This force here is just wasted. You're just trying to push this into the ground and it's not going. So here's a rescue simulation or practice for someone on a chairlift. They've thrown the rope up over the cable, put a harness on the guy there, and this guy over here is going to lower them down. Well, what could go wrong? Well, let's treat his weight as a vector. So if he weighs 150 pounds, there's 150 pounds pulling down on him there. That force is going to be transmitted through the rope and be 150 pounds on him here. This guy here has not thought fully about the direction of the force, because we've got a large amount of force on him in this direction, and it has a component to the right and a component up. He may have only been thinking about the upward component, and since that is a shorter vector than this, the force trying to lift him off the ground would be less than what this guy weighs. But what he forgot was that this force here has a component to the right. Let's see what happens.
Start lowering you straight to the ground. Very good, perfect. I'm right below you here. I'm coming down. Watch it. Ooh. You okay? Yeah.
You can't forget to think about the direction of the forces. So here's a person pulling a wagon, and you can see from the way his arms are hanging, the direction of the force is going to be in line with his arms. So as he's walking forward, trying to pull this wagon down the street, the force that he's applying to the handle of the wagon is in this direction, and it has a component this way and a component that way. So of the force that he's applying, there's only this much force pulling in the direction he's trying to go. All this force is just trying to lift it off the ground, and because this is heavier than that, it's not being lifted. He could have made one simple change, and that would be to lengthen the handle here. Maybe tie his belt around the handle and pull on the belt or something. This vector here was the original vector, and then the force pulling along the ground didn't change, but because this angle was so much smaller, the force that he had to pull was a lot less, and it would be very noticeable. If this vector here represented 100 pounds of force, this one may, according to the scale, represent only maybe 70 pounds of force. Now we're going to put angles on this. We're going to actually measure the length of them instead of guessing at what the scaled length represents. But SOHCAHTOA, the sine of an angle is opposite divided by hypotenuse. Cosine of an angle, adjacent over hypotenuse. And the tangent of an angle, opposite over adjacent. There are three trigonometric identities. So if I had a force, which is a vector quantity, magnitude and direction, 250 pounds at a 39-degree angle, there is a component horizontal and a component vertical, because you could have described that force as being to the right and up. Well, if I know the hypotenuse and the angle, I could use sine. The sine of that angle is opposite over hypotenuse. Okay, and I can use that equation to solve for y. To solve for y, you got to multiply both sides by 250. This was an angle in degrees, so make sure that your calculator is in degree mode. When you do that, you should get 150 pounds. So of the 250 pounds in that direction, we got 157 pulling up. All right, now we can find out the horizontal because the cosine of that angle is adjacent over hypotenuse. And the same thing, we're trying to solve for x, so we got to multiply both sides by 250. And then I'm going to 250 multiplied by the cosine of 39, I get 194 pounds pushing back in that direction. And you know, that's a bigger number than that, and we can see it's a longer side than that. This situation where we know the angle and the hypotenuse, and we want to find both components, that is a very, very common situation. So common, I'd like you to be able to take a shortcut. Skip this step altogether and go straight to this step. Just say, hey, look, that is going to be 250 times the sine of 39. This is going to be 250 times the cosine of 39. You'll get the hang of it. So let's do it with this one. If I had 75 pounds in this direction at a 29-degree angle, we want to draw in the components. So we're going to start at the tail and go straight down until we are horizontally in line with the head of this and the head of this. And then we just draw in our horizontal component. And since that is a right angle there, we can use our shortcut now. We would use the hypotenuse times the sine of this angle would give us this side. Your calculator would have just said 34 pounds, but I threw in a negative there because I realized that's in the down direction. This force is down and right. And now let's calculate this one. 75 times the cosine of 27 and 67 pounds. I left it as positive because to the right is positive. If it had been off to the left, it would have been a negative. All right, so that was a situation where we were drawing horizontal and vertical components, and those would be like relative to the ground. If I had a ramp here and I wanted to draw components relative to the ramp, I'd have to kind of rotate that whole triangle and find out some that is not vertical and horizontal, but parallel to the ramp and perpendicular to the ramp. So I wanted to take the force of gravity, which is straight down, and find a component that's parallel to the ramp and a force that's perpendicular to the ramp. And you think, what are we doing? So let me explain. Let's say that we have a big ball on that ramp. And I'm saying that's a big ball because it's 75 pounds worth. Let's get practice drawing the components. Before we started at the tail and we drew that line until we were horizontally in line, but let's just go ahead and draw that line until we are perpendicularly in line. I'm not sure that's a word, but I think I'm communicating at least. So we drew it until we were perpendicular to this, and then we just finish it off by drawing from this head to that head. These are the two components. All right, so what does that mean? What would happen if a guy's standing there and he's wanting to keep that ball from rolling down the ramp? Well, the ball weighs 75 pounds, but he doesn't have to push with 75 pounds. There's only 34 pounds in this direction, so he just has to push up the ramp with 34 pounds. Now, what does this one mean? If we were to put that ball on the scale when it's on level ground, the scale would read 75 pounds. But when the scale is on the ramp, and we'd have to maybe glue the ball to it so it wouldn't roll off, we're trying to measure the force that is against the scale, and that's this component. So when it's on the ramp like this, we would measure 67 pounds on that. All right, one more piece to this type of problem is often I would give you this angle and you wanted to find this angle. Well, I've already given you this angle, and the relationship between these two angles are going to be the same. So let's just work backwards. Knowing this angle, let's find this angle. We have a triangle here. We're going to outline that in red, and we're going to call that our white triangle. And then inside here we have a yellow triangle. Well, this for the white triangle is a right angle, and this for the yellow triangle is also a right angle. This angle for the yellow is shared by that angle for the white. So we have two angles of the yellow triangle congruent to two angles of my white triangle. So the third angle must also be congruent. So this is the third angle of the yellow and the third angle of the white. They must be equal. So when you draw gravity pulling straight down here and you find a component this way and a component that way, whatever this angle of the ramp is, that angle is going to be the same. And just to help you, we can extend that triangle and see that those angles work out the same way as well. All right, before we get into too complicated of a problem, let's just talk about equilibrium. Equilibrium is just something that's not moving. More importantly, it's not accelerating. We're going to save some of those details for Newton's second law. But if something is in equilibrium, if you add up all the forces, the combination of all the forces will equal 0. Another way of saying that is that the sum of all the forces is 0. Sum is just the addition of everything. Or we have a Greek letter sigma here. Don't be frightened by that. That just stands for, that just stands for add up all the forces and they should equal 0. Another way of saying that is the net force equals 0. All right, let's look at some examples. Let's say this person is hanging from the bar here and they weigh 60 pounds. And I put a negative there because it's in the down direction. She's hanging from both arms, so probably each arm is supporting 30 pounds of her weight. So the sum of the forces equals 0. 60 down plus 30 equals 0. What if they didn't hang from both arms, but hung from all three arms? Could happen. So let's say that 60 pounds down, each arm this time would probably hold 20 pounds. So the sum of the forces equals 0. All right, here we have a table. The table weighs 20 pounds. We have a 90-pound anvil sitting on the back left-hand side of the table. So this leg has to support more of the weight than anything else. But I want to figure out how much force is supported on this leg. It is just minus 90 and minus 20 and positive 30 and positive 50 and positive 20 and a positive question mark to equal something here. So the sum of the forces equal 0. Looks like if you add these all up, question mark is going to equal 10 pounds. So if you load trucks too heavy, they can put damage on the road. So we have weight limits, depending on the number of axles they have. And you don't have to weigh that. Let's say a police officer was going to pull you over to the side and make sure you weren't overloaded. You don't have to have a scale that will hold the whole truck at once. You just need to weigh either one tire at a time by driving it up onto a scale, or if you had a big enough scale, you could weigh it one axle at a time, because all those upward pushes measured by the scale should equal the one downward force, the weight of the truck. All right, let's apply that to this situation here. If a mass here has 1 kilogram of mass, it's going to weigh about 10 newtons. It's actually 9.8, but again, we're going to defer to Newton's second law. That's coming up real soon. 1 kilogram weighs 10 newtons. Gravity's pulling down with 10 newtons. The scale must be pulling up with 10 newtons. Just like the person that was hanging from 2 arms, if I had 2 separate scales pulling up on that, gravity's pulling down with 10, each scale would be pulling up with 5. So the total up and the down all add to 0. But now here's where we're switching around. This is where we get more into the vector nature of equilibrium. What if I had a weight here hung from 2 scales at a big angle here? Well, the force in that direction has a component this way, and the force in that direction has a component this way, and it has a component up. Gravity's pulling down with 10 newtons, so this one has to be pulling up with 5, and this has to be pulling up with 5, so that all the forces in the up and down direction equal 0. Both of these equal 5 only because this angle and this angle are the same. We'll do a problem that's more complicated here in a minute. The thing to understand here is that this force here, if this was 5, that's 5, 5, and 5, so the scale might have to pull up with maybe 16 pounds, just 5, 5, 5, and a little bit more over there, a little over 15 pounds, we'll say. So it had to pull with over 15 pounds of force in that direction to get 5 pounds in that direction. There was a lot of wasted force pulling to the left here and pulling to the right here. But here's where we can formally say that if this is just hanging there in equilibrium, not just the sum of the forces, but the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. Gravity pulling down and those forces pulling up should equal 0. This force pulling left and that force pulling right should equal 0. Let's do this not as components, but as just simple addition of vectors. So if we have gravity pulling down on something, to be in equilibrium, we need an equal amount of force pulling up. We could achieve that force if we had two things pulling straight up of half the weight. But if we had things pulling off at a little bit of an angle, this force added to this force, and I'm doing this tail to tail using the parallelogram method, this force added to this force results in that force. So that those two forces would be in equilibrium with the weight. If those forces were at a bigger angle, now they're pulling more to the right and more to the left, but this vector is longer than this vector, which represents this has to be more force. As we pull at even greater angles, this force here pulling off in that direction is actually longer than the weight of the object itself. And if we pulled bigger and bigger and bigger angles, the forces would have to become very, very, very large. We'll calculate that with this equation we're going to develop. Now there's symmetry here. This is a 30-degree angle and this is a 30-degree angle. So this rope pulling in this direction has a component up and a component across, and so is this rope over here. What do you think that component should equal? Well, you might think 100, but it's actually only 50. The reason is this rope over here has a component up and a component left, and it provides another 50. So to get this rope was what was holding the crate, and so is this one, and we're trying to find out what would be the tension in that rope. How hard do you have to pull in that direction to be able to get 50 pounds in that direction? Well, it was a 30-degree angle, and we covered in another video special right triangles, 30, 60, 90. The hypotenuse is twice the shortest side. The shortest side is opposite the 30-degree angle. So if this is 50, this side here must be 100. 100 pounds that way plus 100 pounds that way results in 100 pounds that way, which balances our 100 pounds in the down direction. Well, let's see what equation we used, because we're going to do it not just with 30 and being able to use special right triangles, but the sine of this angle, which is 30 here, is opposite over hypotenuse. Okay, and I want to find out what that is, so I can multiply both sides by question mark, divide both sides by the sine of 30, and if I just take half the weight divided by the sine of the angle, it would tell us the answer. So let's do it now with not 30 degrees, but 10 degrees. Same thing, we've got tension here, which has a component up and a component horizontal. This one has to be pulling up with 50 because that one is pulling up with another 50. The sine of 10 degrees equals opposite over hypotenuse. And then so we want to find out what that tension is. We're going to multiply both sides by the tension, divide both sides by the sine of 10, and we get 288 pounds. When these ropes only sag by 10 degrees, you have to pull with 288 pounds that way and 288 pounds that way to be able to lift 100 pounds that way. All right? And that's just the equation we're going to use for the rest of these as well. Instead of 10 degrees, it's 5 degrees. So to be able to lift 100 pounds, the tension has to be 570 pounds. If we pulled these ropes super taut, so that when you hung the 100 pounds on there, only sagged a little bit, you'd have to pull with almost 3,000 pounds of force in that way and 3,000 that way to lift 100 that way. So if we have a whole bunch of people pulling on the rope in tug-of-war, you can get a lot of force. But let's hang a bowling ball on there. Do you think the rope is going to sag down a little bit like this? It may not seem like it does, but it has to. Because if gravity's pulling down on that bowling ball, the only way for it to support that is if the rope is pulling up with some component. Still, this force and this force pulling in the up direction have to balance what the bowling ball is doing here. Now maybe it wouldn't sag as much as I've shown here. What would happen if I put a feather on there? Would the feather make it sag down a little bit? It turns out yes. Probably imperceptibly, but it would still sag down. Because if the feather, let me come back to here, if the feather was sitting on here, gravity's pulling down on the feather, you still need an upward pull. And you can't have an upward pull or an upward component if that angle is 0. It has to sag down just a little bit. So if I had two big diesel electric engines pulling as hard as they can on a very strong cable, and you put a little feather there, it's going to sag down a little bit. Okay. Now that cable itself is heavier than a feather, so the cable is going to sag down under its own weight. And that's what happened here, is that these power lines or telephone lines were hanging here, and ice collected on them, and they were hanging pretty straight here, so when you added weight to the cable, it became such large forces that down this way the cables broke and everything fell this way. And if you tie a cable between here and here, you would be surprised at how much force is in tension in that cable. Certainly surprised this guy. If you watch that guy, you can see he really got surprised. Uh-oh. Seemed like a good idea, but he didn't take into account vector forces. What about just like hanging wet clothes on a clothesline? Those would be really heavy, and that clothesline could easily break if it was pulled too taut. You always have to have good slack in the line. And maybe your clothes got dirty, but if the cable broke, but you would lose your life if the cable broke here. So that would be a Tyrolean traverse is what that's called. Slack line, the forces in this cable are huge. Zip line, you've got to consider the forces. So let's see how we would calculate those. First thing we need to do is talk about free body diagrams. That when this runner's accelerating off that way, a free body diagram, let me just back up here a second. A free body diagram is just identifying all the forces that are acting on that person as if the person is one spot, one little dot here. So gravity's pulling down on that person, and the leg was pushing the starting block that way, but the starting block was pushing on the person this way. So that would just be a free body diagram. Let's do it with this one. So here we have this beautiful chandelier. It's a Chihuly, very expensive, and it is our job to dust it. Normally it just hangs straight down here off in this area, but we needed to pull it off to this side so we could dust it from the balcony here. And I'd like to calculate how hard do I have to pull and how much tension there is. So that is a free body diagram. We got the one rope pulling off in this direction, another rope pulling off in that direction, and gravity pulling down with 650 pounds in that direction. That's your free body diagram. If you're asked to draw that on a quiz or a test, that's what you draw. But remember, the sum of the forces in the x direction have to equal 0, and the sum of the forces in the y direction equals 0. That's a little bit in the x and a little bit in the y, so we have to find components in the x and the y. When you draw components, it's no longer a free body diagram. So if you're asked to draw a free body diagram, don't add components to it. You might have to redraw it to solve the problem. And if you draw those components, you have to cross out that one because that tension has become these two vectors. And I want to find out what they are. So this pull to the right should equal this pull to the left because it's the sum of the forces equals 0. And the pull, there's only one pull up, and it has to be balanced by this one pull down. The tangent of this angle is equal to opposite over adjacent. So I can find out what this one is by the tangent of the angle, opposite over adjacent, multiply both sides by 650, and you find that this one's going to be 410 pounds, which means that one also has to be 410 pounds. We got to pull with 410 pounds that way, which means you might not be able to do that by yourself. Okay, so now we got to find out this tension. We could use Pythagorean's theorem with those two to find this. I prefer not that method because this had a lot of decimals that we just threw away. It's better to go back to our original data. So I'm going to say the cosine of this angle is adjacent over hypotenuse. Multiply both sides by t, divide both sides by the cosine of 32, and you get 770 pounds of tension in that cable there. All right, I promised we would do this problem, so let's do it. We're hanging from this hammock, and we want to find out how much tension is pulling this way and how much tension is pulling that way. These angles are not equal, so it's a little more complicated. We're just going to zoom in on just that part of it. Here's the free body diagram, and there is a component to the left and a component up, a component right, and a component up. Now that shortcut we use with sine and cosine, this horizontal component can be this tension times the cosine of this angle, T1 times the cosine of 9. I made it negative because it's off to the left. And this component here is going to be this tension times the cosine of that angle. Those are the only two forces, and they have to add to 0. In the y direction, this is pulling up, and T1 times the sine of that angle would be that component. T2 times the sine of that angle would be this component. And then we have this pulling down as well. Challenging thing here is that we have T1 and T2. We have two variables, so we have to use two equations. We will solve this equation for this variable here. I'm going to add that term to both sides. It's going to show up over here. I'm trying to get T2 by itself, so I'm going to divide both sides by the cosine of 21. So that's what I get here. So I've solved this equation for one of the variables. Now I'm going to substitute that into right there. So instead of saying t sub 2, I'm saying all of that. Now if you're in geometry now, or haven't had algebra 2 or trig, this you might not recognize, but the sine of 21 divided by the cosine of 21 is the same thing as the tangent of 21. So I just simplified those two things and called it tangent. Still trying to find out what T1 is. So we're going to add 180 to both sides. And then there was a T1 here and a T1 there. I'm going to factor it out. And so I'm just left with all of that. I can solve for that if I take 180 divided by all of that stuff there, and I would get 336 pounds is how much tension is pulling that way. Now I want to find out how much tension is pulling that way. Well, this equation can do it. We just plug in 336 there and then solve for t sub 2, and we got almost 360 pounds. Remember, this person only weighed 180 pounds. We needed twice that amount of force in that direction to get enough force pulling up to support his weight. That's a little bit with equilibrium and using components of force vectors.